What I want to discuss is what I titled here as commonalities and otherwise not so common things across various combustion systems, because you must know some fundamentals are the same across various combustion systems, and we will address them. There are some things which I say which have already been must have been said by Varun. So, some overlap like this will be there, but I will say it some way, he will say it in some other way, and you will understand in a third way. Let us look at what I consider general behavior of premixed and diffusion limited flames. I summarize them: turbulence and its role in premixed flames, diffusion flames and in some complex flows, and there are some questions which have been brought up. We will address them separately, but you kindly listen to this as we go along. Those which have been posed, written down and given, will be addressed separately. We look at some droplet combustion physics briefly. Again, overlap may be there. Injection system, diesel engines, direct injection gasoline engines, and monopropellant liquid thrusters, bipropellant liquid engines, combustion chambers, injection strategies and so on. This take a role of chemistry in ignition, steady combustion and extinction. Again, a bit of overlap. The behavior of premixed and diffusion flames. There are two cases here: a flame which is jet fuel air mixture coming out, and there is a flame here, fuel alone coming here, air is around, quiescent shall we say. It could also be flowing, but let us in this case treat it as quiescent. So, air is drawn in and you will get a flame around. Let us look at the features. This is the premixed flame front which has been shown to you earlier as well. This is the post flame oxidation and radiation zone where you get a look of the flame. Fuel air oxidant are together. Therefore, air to fuel ratio, or what you call the equivalence ratio, is the key parameter. It defines the flame temperature, because the flame temperature will depend on the equivalence ratio. Since diffusion is fast, chemical rate controls the combustion process. Burning velocity is a reflection of this aspect. The flame has features like flammability limits, flashback, blow off and quench. These are features of premixed flames. As different from this, if you look at diffusion flames, you see there is a zone where there is no oxidizer but only fuel. There is a zone where there is no fuel but only oxidizer. So, they are not coexistent in the larger sense. They exist, if at all, at near the surface, so called surface, but it is a small thickness discussed earlier. Situation is not different in the case of liquid drops. You have seen the pictures as well. This feature which you see is valid for 0G. There have been excellent experiments done by Japanese researchers. Some of them have visited this institute as well, taken photographs of this flame, beautifully spherical flames around the droplet. And if you take 1G, which is ambient conditions, you will get a flame like this, which you also have seen. In this case, fuel and air are separated by a flame, diffusion is slow, and when fuel and oxidizer meet, they instantly react nearly, and therefore high rates. The flame is located wherever. Now, this is the key point I want you to recognize. The flame is located wherever the fuel and oxidizer fluxes along a local normal or in stoichiometric proportions. You must see every word has a significance when you go and look at complex flows. The flame may be very complexly structured, but you will discover that a diffusion flame is located, and if you take a local normal and you see fuel on one side, oxidizer on one side, the ratio of the fluxes into the flame will be in stoichiometric proportion. For gaseous fuel injection, the flame location adjusts itself depending on the flow rate. So, if you put more flow, the flame will be longer, the flame will also go. For liquid or solid fuels, which is what matter of concern for discussion later, the air to fuel ratios for stoichiometry controls the flame standoff. Since the oxygen to fuel ratio is large, as is true for most hydrocarbon 15, 16, 17, the flux demand leads to flame standoff several times the fuel size. If you take here 1 mm drop, typically this will be around 10 mm. Typically, flame temperature in this case is the adiabatic flame temperature, affected mildly by stretch and other effects. Now, what I mean is, as distinct from a premixed flame, where the flame temperature is a function of oxidizer to fuel ratio or R equivalent to idea equal to equivalence ratio. Here, all equivalence ratio means only stoichiometry. Equivalence ratio for a diffusion flame is only 1 unity, and the temperature at the flame is stoichiometric. This is very key to some of the points which we also discussed in the case of gas turbine engines earlier in the day. Let us look at the role of chemistry in ignition, steady combustion and extinction. Steady premixed combustion in multi-dimension depends on chemistry as much as it does in the one-dimensional case. There is no distinction there. In the one-dimensional case, the burning velocity can be taken as representative of chemistry. Sometimes the question was asked earlier, can we measure the reaction rate? It is important to, this quickly comes to my mind, we talk so much about reaction rate. What is reaction rate? Reaction rate is the rate at which two of the reactant lead to the product. How do you measure the reaction rate? You measure the reaction rate by its effect. You do not measure the reaction rate. What is the reaction rate? It occurs at a molecular scale. What you see is a result. When reactant changes in its content, magnitude, something else gets formed over a period of time, in a space mode as well, there will be changes. You need to factor all the features involved to get the elements involved in the reaction rate. To state it simply, let us say hydrogen reacts with oxygen to get you water vapor and some other products. So, if there is a spatial variation, as will happen in every case, a droplet or a flowing jet or whatever, you need to take into account the convection and diffusion. Suppose you say, no, I won't do it, I will take only, let us say take ammonium perchlorate and I want it to get a decomposition rate, I will put it somewhere and allow it to decompose and measure the composition. You have to measure the composition. When you measure the composition, it will lead you to the decomposition rate. Ultimately, the chemical reaction rate expresses itself in change in the composition. You measure the change in the composition with time or space and then factor it into a expression, you will get the reaction rate. Therefore, what is meant is the measurable quantity is the flame speed or the burning velocity in this case, and so it is a representative chemistry. It is just semantics. Would you like to treat chemistry as the reaction rate as more fundamental or burning velocity is more fundamental? We can keep discussing till any point of time, but what you measure is burning velocity. You know a number. So, you can say that hydrogen oxygen mixture with its flame speed of maybe 2.5 meters per second is more reactive than methane air mixture with a flame speed of 0.4 meters per second. You can say that very clearly. Keep this thought in mind. In engineering, what is more important is what you measure. Then you can deduce many things consistently. So, there are other features which will influence the premixed flame or diffusion flame, something called stretch, which we will define a little later, and of course turbulence. Both of them will influence the burning velocity, and therefore most observations of what you see in reality can be understood within this framework. Burning velocity justifies single step chemistry, which is what we talked about here. That is, if you know the burning velocity and you can connect it to a single step chemistry with some activation energy and frequency factor, and this will be a good choice for the computation. This is in fact the strategy for modeling solid propellant combustion, which Dr. Varun will speak tomorrow. It will be adequate for other premixed flame situations as well. Unsteady or unstable premixed combustion near limits of flammability can be dealt with by using additional features of fluid mechanics as in flame blow off or flashback. These are phenomena which occur and is related to flow rates, and so you must factor into it the fluid dynamics in some form. And once you combine them, idea of burning velocity with mixture ratio, whatever, all that will fall into place. Diffusive combustion, near limits of extinction or ignition, need chemistry. This chemistry, whether it should be reasonably substantive, multi-step chemistry, where number of species and a large number of steps, is not necessarily identical as what is used for premixed chemistry. Premixed chemistry has a whole structure. It's not clear that it is identical to what happens in diffusion flames. There are differences which we have ourselves observed, including Varun, but I think these are still need to be examined. Actually, it's not been examined very much because diffusion flames depend on chemistry not very much except for emissions, for which case you need to create models for extracting the information on the emissions. That's done specifically for that purpose. So, the role of chemistry has been used in the literature, but it's not obvious everything is hunky-dory. Steady diffusion limited combustion can be taken to be relatively independent of details of chemistry when it comes to burn rate or many such larger features. There are issues like auto ignition and ignition in practical systems. They need to account for the conduction of heat or diffusion of species and need to treat both diffusion and reaction processes. Ignition or extinction, they depend on chemistry. Steady combustion in diffusion flames is not dependent on chemistry. This simple rules of thumb can be integrated into your mind on a continuous basis. Okay? Because quite often when some things happen in practice, you will be confronted with the situation, chemistry must be important, something like that. When you do the experiment, you will find no difference. Why is it there is no difference? Difference is not there because its role in terms of larger heat flux distribution and mass flux distribution is not very much. Emissions, yes. That's all the point we have to keep in mind. Let us look at some examples of premixed flames. Premixed flames, in the best definition possible, is just that you have something to make the flow uniform, okay, and then something to make the velocity distribution here uniform. Then you light it, you will get a flame here, nearly flat, but it's very sensitive. You should be very careful in dealing with it. Small changes in the flow rate can either blow it off and make it stick to the wall. So, this is one example of so-called one-dimensional flame. But if you increase the velocity to a fair extent, you will get a conical flame. But then the point is that normal to the surface of the flame, if you measure the velocity in the cold side, there are velocity differences in the cold and the hot related to the temperature ratio. Very simply stated, the mass flux is the same across the premixed flame, normal premixed flame. Therefore, if you have rho u SU here, rho b SB. Rho b the density on the burned side, rho u the density on the unburned side. Unburned side typically may be 1 kg per meter cube, on this 0.3, 0.4 kg per meter cube. The ratio is related to essentially flame temperature ratios. Therefore, you will discover that the flame speed normal to it will, even in a conical flame, will be equal to the typical value for methane air, 0.4 meters per second. You will still discover that number, though the flow rate here is much equivalent velocity is much larger. In this case, you will get identical to flame speed. In this case, the velocity may be larger, maybe even 1 meter per second, but normal to it will still be 0.4 meters per second. Okay, then this is one way of doing that, and quite often there are many methods people have tried. There is one of our former students who is a professor in IIT Bombay, Sudarshan Kumar, and he has done lots of extensive pieces of research on many techniques, and one of the techniques he uses is here, diverging flame, and you get a one-dimensional flame, you make measurement of the velocity here, it gives you the flame speed. And people have also used it's called opposite diffusion flame. You use a fuel and oxidizer combination from one end and the other end, light it, you will get a flame, and if the product gases go out like this. This also gives you a result, but these things are related to the following fact. In this case, flame is virtually flat, flow rate normal to it. In this case, around the top cone, you will find the diverging streamlines. Same way here, you have diverging streamlines. When you have diverging streamlines, you have a velocity along the axial direction parallel to the flame. Now, that gives you stretch. As you keep increasing the velocity, this stream velocity, you will get stretch effects in this direction. The stretch effects sometimes are positive, sometimes are negative, and there is a whole theory for that, stretch flames. Okay, this is one part. Now, you can measure the composition as has been done by somebody else of oxygen, of methane, and many other species. And this is not the result of a compositional measurement, but this is the result of a calculation. But people also have measurements for many of the major species. I want you to look at some principal features here. Since it's a premixed flame, you will find both oxygen and methane keep coming down and comes down to low values here. Then you will find a product going up like this. You see a very interesting feature. The temperature goes to around 1800 K or so and keeps on. The other 200, 220 K takes a long distance for it to reach. There is something very peculiar about it, and you can express it in another plot where you find a heat release rate plotted as a function of dimensionless temperature, which is what? The actual temperature minus T naught at the initial temperature divided by the adiabatic flame temperature minus T naught. If you take this coordinate, you will discover that with a full chemistry, if you calculate, the reaction rate drops around 0.8 of this dimensionless number, and slowly the temperature keeps increasing beyond that point. This is a feature not only of methane, of propane and many other species, and actually has not really been addressed in the literature or the consequences. Maybe it does not have too much of an effect and therefore has not been addressed, but it is something very peculiar. It is normally you tend to think it will reach the equilibrium value right away, it will not. The actual flame zone thickness, you can measure it by looking at the reaction rate plot here. In this case, it is a very small number, about 0.5 millimeter or so. So, let me summarize the facts as you see here. The velocity normal to a one-dimensional flame of premixed reactants is called the burning velocity. First statement. There are several techniques to measure the burning velocity. It is a function of equivalence ratio, pressure and initial temperature of the reactants. The variation of the reactants and temperature of the flame has actually been measured, consistent with what you see here. Typical flame thickness for a methane air is 0.5 millimeter, and it is completely different for others. For hydrogen air, it will be much lower than this. Efforts to get equivalent single step chemistry parameters show that it can only be approximate. You cannot get a single step chemistry expression which actually matches with this. But if you match this, you will get an activation, something called an activation parameter, which is the activation energy divided by gas constant times the adiabatic flame temperature. And this is taken usually as infinity in the asymptotic analysis, and it is about 6.3 or so for the stoichiometric case, and actually for the methane air case, it is much lower for hydrogen air flame for stoichiometry, it is about 3 or so. But for lean limit ranges, it will probably much larger, about 15. Well, this tells you how we estimate the parameters of a single step reaction. Locate the non-dimensional temperature at which you get the peak reaction rate. From that, you can extract the equivalent activation energy and so on. There are numbers which are quoted here. Not very important. Yeah, please go ahead.
And then I started plotting the profile which is being done. Will the structure still remain the same as it's been explained here?
No, the matching of the flame speed is the first thing which will happen.
Okay.
This is, see, because you have actually one free parameter which is the activation, the frequency factor. The frequency factor is essentially proportional to flame speed. So, there is no difficulty. See, there are two things. When you say flame speed, it is the integral feature of this particular curve. Therefore, that is no difficulty in terms of expecting it to match. This is the detail as to how the reaction rate varies with temperature, and that matching is slightly more involved, consistent with the fact that you have the flame speed.
In perspective of kinetic theory, we have been discussing about temperature as measurement of the energy content of a molecule, and the frequency factor is the collision frequency between two molecules, which can lead to the reaction. And coming to this frequency factor, reaction rate linear relationship, and the temperature reaction rate relationship, which should be more predominant to get a better mark. It's like a temperature or the frequency factor, because both are interlinked, and we are looking at different perspective for the same.
No, we are not looking at different perspective. Both are involved in calculating the flame behavior. In terms of an average, you will get the flame speed. Average means integral of this gives you the flame speed. In terms of the variation of the heat release rate or the distribution of it with temperature, you will find the activation energy plays a role. If you take a full chemistry calculation, you have no freedom. You do not have any freedom when you take full chemistry, because each of the steps is a molecular event, and for that molecular event, people have obtained both the activation energy and the frequency factor, and forward rate, backward rates are all available in literature. Chemkin gives you all the information, and you can use that and compute the full flame structure from that. So, there is no independence for you to do anything at all. But insofar as approximation is concerned, what is being said is the flame speed is related to average reaction rate. You saw Varun present it in the morning. Okay, what is average reaction rate? Average reaction rate is a frequency factor times of a variation of the over the domain of the e to the power of minus a by RT in the rest of the terms. Therefore, that part and the frequency factor are two quantities. That second part is dependent on activation energy, the first part is dependent on frequency factor. If you say it is proportional to flame speed, the frequency factor is a reflection of the flame speed. The variation in temperature of the reaction rate is dependent on the activation energy. So, that is how you should look at it. There is independence in each one of them, and there is no conflict. Yeah. Here is the data from measurement which sent by Sudarshan Kumar. You will see for methane air a large amount of data of the burning velocity with equivalence ratio, and you can see 36.36 meters per second being the mean number. They have done experiments for various pressures, initial temperatures, and so on and so forth. You have numbers with increase in pressure, the burning velocity comes down. Recognize that. And with higher initial temperature, the burning velocity increases. This is for isooctane. You see at 360 and 470 Kelvin, the burning velocity is high. It's about nearly 78 centimeters per second at 470, and at 360 Kelvin also it's higher, 45 centimeters per second, whereas for methane air it's about 36 centimeters per second. These numbers for hydrocarbons between 36 centimeters per second to 40 centimeters per second is common for all hydrocarbons. As a function of pressure, flame speed comes down. As a function of initial temperature, it goes up. This can be stored in your memory, no problem. Actual numbers, you will see the results. Okay, little more of the detailed discussion. We will see very quickly back of the envelope calculation in this matter. Please pay attention to some details. This is the conservation equation for the mixture for the fuel fraction inside the flame. M dot double dash is nothing but the mass flux, convection term, diffusion term, reaction term 1, 2 and 3. Now, the flame, this just shows that the temperature is increasing and going here, and this is the flame thickness. Now, if you take convection reaction balance, that is 1 and 3, just look at this, rho u times dyf is 1 minus 0, okay, divided by delta f. gives you the average reaction rate, some number. So, you will say rho u by delta f is the omega and gives you rho u equal to omega delta f. Okay? I mean, by definition, this is only other terminology, that is all. If you take diffusion reaction balance, you say this balance is this, then it tells you rho d 1 minus 0 by delta f square, d by d x is here, x is also here, delta f square gives you omega. So, this tells you rho u, if you couple this with this, you will get rho u delta f is equal to rho d. Rho d is also the same as k by Cp or mu. If you say Prandtl number is equal to mu by Cpk, whatever, and Lewis number d rho Cpk by k equal to 1, they all tell you rho u delta f is equal to rho d or k by Cp. So, this gives you rho u equals to rho d into omega under square root. Why does you get square root? Because you see here delta f square and you can take it to the other side, delta f is rho u by omega, combine them, you will get this result. This is exactly what was discussed in the morning. And if you can express it in explicit form, the mass flux through a premixed flame is proportional to root of k by Cp, p to the power of n by 2 and exponential of e by 2 RTAD. So, all the terms related to chemistry are involved here, and the fact that rho u delta f equal to mu also implies there is something called flame Reynolds number, which is essentially rho u L by mu, rho u delta f by mu, that is equal to just 1. So, the flame Reynolds number is 1, and the fact that the flame speed is proportional to the square root of the reaction rate is explicitly brought out here by simply a convective, diffusive, reactive balance. More rigorous analysis is possible, some of it may be done here itself, let us see. But it should be realized that since the frequency, I mentioned whatever we discussed a little earlier, since the frequency factor is never known to any degree of accuracy for an equivalent single step reaction, this expression can be used for scaling pressure and initial temperature effects, but the measured value of the burning velocity is the only quantity of true significance, a point of view which we were discussing a few minutes ago. Okay, there are other aspects of flames which we must also appreciate. If you take the normal case that we are discussing till now is an unburned gas coming out with some speed, going out the burned gas with speed which is the ratio of the densities. But suppose you create a little disturbance at the surface by turbulence, by some other means, then the flame becomes curved and you will find two kinds of curvature, conical and convex. This will have influence, and to one order you can say the reaction zone thickness does not change, and you can make a calculation of what the role of the curvature also is. So, curvature has an influence on the burning velocity. So, the one dimensional flame is unstrained. Any curved moving flame will have positive and negative stretch is what I have said here. What is positive and negative stretch? There is a flow velocity which occurs along the flame, which is 0 here, and that variation with stretch is 1 by second, which is called the strain rate or stretch as is classically called. Okay, and this stretch can come from many sources. You can have a flame which expands, and because it expands, as I mentioned a little earlier, there is a velocity along the axis of the flame and that changes. So, you will find variation of that gives you a stretch. Okay. Spherical flame. The spherical flame is always expanding if you spark it at the center, and therefore, the area keeps increasing, that area imposes a stretch rate. Because the same flame is trying to move it to larger and larger diameters, and therefore, there is a stretch involved in the process. So, also axisymmetric flame near its core axis also will have compression here. Okay. These are aspects imposed on the premixed flame, I am telling you, additional features. You can also be doing swirl you can have a swirling premixed flame. If you have swirling premixed flame, you will discover very peculiar effects which have also been experimentally studied. If you look at the flame here, it turns out that at one zone you will find that because of the swirl there is a certain variation of pressure with the radius. Because of the swirl, the pressure is higher here, lower here. Okay. But when the thing is burnt up here, that variation will not be as much because of the flow expansion. So this creates a difference in pressure which actually causes a motion of the fluid into it. So much so that you will discover the flame speed versus the tangential speed to be very significant. You find the flame speed in such situations very large. As you can see from experimental data here, if you create 10 meters per second of tangential speed, the flame speed itself becomes 10 meters per second, whereas 0.4 meters per second is 10 meters per second. And it is not as though you are creating one experiment where there is a tube and you create a swirl and then you examine what happens. That has been done here. But suppose in a complex flow, you have somewhere a little swirl created, the flame will get burnt up very fast locally. These phenomena which you see as a separate experiment are embedded in an actual flow. It can happen very easily. You are always have swirl in many situations. Sometimes the gas in a rocket engine in the central port is introduced with swirl, sometimes without swirl. You introduce kerosene with swirl, usually in many situations. In the case of gas turbine engines, swirling flows are most common. The air is introduced by a swirl to create a recirculation zone. Sometimes liquid is introduced as a film in a swirl mode, and you will discover this swirling flow in a evolving complex flow might have locally structures which have got a swirl. And this phenomenon which you see here can occur there as well, which of course is captured by the calculation. But if you must know why certain thing has happened, and the burning velocity here is, or the so-called the velocity at which the consumption takes place, the flame velocity is much larger here. That is something that you should keep in mind. I have here data simply put together from several mixtures. So, this data varies slightly depending on the position you choose for locating where the flame maximum point is and minimum point is. You will see as a consequence of say mixture ratio change, the flame thickness changes. For the stoichiometric flame is very small here, and for lean and rich it is larger, and for hydrogen air it is, the numbers are smaller. Right? These are features which we have discussed several times. Yeah.
The Torah structures maybe behind the backward circuit step of the as you said, it has increased the flame speed nearly 10 times or 8 to 10 times. And what is the physical interpretation that we can take?
I have shown you the physical interpretation right here. Suppose you take this as a tube, cold unburned gas is coming like this swirling. Okay. You put a spark here. Technically, if you had a tube in which the gas was present here, coming at, let's say, it's 0.4 meters per second. If you had simply ignited here, the flame will stand there because one dimensional case, flame speed and the flow velocities are same, so it will stabilize here. Yes. And if you give this velocity a little lower, the flame will move into it at a different speed. Yes. Speed difference between the flow speed and the burning velocity. Suppose 0.4 meters per second is coming here, the flame would stick here. If you give 0.3 meters per second and this is 0.4 meters per second is the flame speed, this flame will move into it at the rate of 0.1 meter per second.
Yes.
And if this flame, this velocity is, let's say, 1 meter per second, this flame will curve into a cone. It will not blow off. Maybe it will blow off if there is no place where it can attach. But if it can attach, you will find a conical flame where the normal velocity will turn out to be 0.4 meters per second. These are classical. Yes. I am saying in this tube, suppose you are doing a swirl and you ignite it at this end, the phenomena which take place I have shown you here. Under normal conditions, this unburned gas, the pressure will be low at the center compared to that at the boundary, because swirling centrifugal action makes the pressure higher than at the center. If you just swirl air into a duct, you will find suction going in. Okay. Now, once it burns up, in that zone, you see the density has gone down locally when it burns up. Therefore, it cannot accommodate, pressure builds up, and that difference in pressure between what happens here and what happens in this domain creates a velocity quite significantly large. This has been measured experimentally, and the only point of view I am saying is, when you take a complex flow, you must decompose it into the structures which may be responsible for what you see, and one of them is this feature. Let us look at turbulent premixed behavior. At one scale, you can describe it. This is one form. Lots of dancing flames at some velocity, and so if you take instantaneous pictures, high speed pictures, and just put them one over the other, you may get structure like this. So, on the scale of turbulence is something which you have to characterize. I do not know whether I have here discussion. Okay, let us look at this and go back to this. This is something which is important for us to discuss. Turbulence and limited diffusion phase, but let us look at turbulence itself. There are many perceptions of difference between laminar and turbulent flow. I am sure as engineering graduates who have gone through, you know some of them things. It's commonly understood that pipe flows are turbulent beyond a certain Reynolds number, 2300. Is it not correct for me to assume that all of you are familiar with that? Yeah. It technically is a wrong statement. Correct statement is, turbulence cannot be sustained below a Reynolds number of 2300. What does it mean? It means, if you can create in a pipe flow at a lower speed any disturbance, it will die. When you cross, what it simply says is, it cross 2300, it will get sustained. But there are lots, this particular issue has got a significance which has some aspects are not still resolved adequately. It is often said that you can get at very high Reynolds number laminar flow too in a pipe. Smooth laminar flow, you can get very high Reynolds number. Subject of debate. But leave that as it is. But this much is clear, that you cannot sustain turbulence below a Reynolds number of 2300 in a pipe is the statement which we should agree to. Now, any unsteady flow with fluctuation is not a turbulent flow. Now, I would like to discuss it in a question answer mode, but let me summarize it so that embarrassments on both sides will be limited. Any unsteady flow with fluctuations is not a turbulent flow. Quite often you say fluctuating flow is turbulent flow. Not true. It could be simply unsteady laminar flow. You have a laminar flow, you can be fluctuating the flow speed. It could be acceptable, but that is not turbulent flow. And a flow with fluctuations like white noise, you have lots of fluctuations with this somewhat similar amplitudes, nearly at all frequencies, is also not a turbulent flow. A flow in which the fluctuations have a power spectrum, that is the variation of the square of the fluctuating velocity with frequency, involving all frequencies, not specific only, and not simply connected to any specific geometric feature. Sometimes you can create an oscillation at specific frequencies. In this case, whether you do it or not, you will find the disturbance, if you decompose it into spectrally by using a fast Fourier transform, you will discover all frequencies. And they have a power spectrum of a certain class. When it obeys that, the flow is turbulent. What's happening in turbulent flow? The fluctuating speed draws energy from the mean field and dissipates it through fluctuations until the final dissipation occurs through viscosity, and that is what we discussed earlier as Kolmogorov scale and so on. And this is true with all fluid flows, and a buoyancy driven flow also can be turbulent. Of course, in this case the convective motion gets sustained by buoyancy. Now, I said this because when you are looking at turbulent premixed flame, you must know what is it we are talking as turbulent flames. Okay, I started by showing you this figure, dancing flames. So, when the scale of turbulence is characterized by two quantities, scale and intensity. Intensity is the U dash, if you say, larger U dash is more intense than smaller U dash. Scale, if you create a disturbance, to what distance is it felt? That is scale. You can measure it by correlation. There are other methods, Taylor microscale by some other method, and so on. Nevertheless, the extent of spatial influence, of a fluctuation is the length scale. Velocity fluctuation is the intensity. Intensity and length scale are parameters which characterize turbulence as we want to use them in here. There are many other features which may be important in flows, but for the discussion here, these are relevant and appropriate. So, when the length scale of the turbulence, which is the so-called the correlation length scale or Taylor microscale or whatever we would like to call it, is large compared to the unstrained flame thickness, then the flame is wrinkled. It is like a sheet which is being wrinkled, that is all. The flame surface area change is taken proportional to the turbulent velocity fluctuation, because what is creating this disturbance is just the velocity fluctuation. A simple-minded approach, you say that these are linearly related. This is how Domkohler started his work. And the point of view that you must know is, when you are dealing with a complex problem to begin with, unless nature suggests complexity, assume it is simple. Some variation is present, let us see it linear. If it is not linear, let it show up. We will accept the final result as the nature gives us. But to begin exploration, this is what is the right thing to do. Okay, because the temperature jump across the flame, I am making a point here. Viscosity increases and the flow may become laminar locally. It can even become laminar locally. Let me explain this. See, you have a flow coming in and other side you have high temperature. Viscosity goes like temperature to the power of 0.7. Did you know this? Gas temperature to the power of 0.7 is the way viscosity increases. So, when the flow comes here and becomes hot, viscosity increases. When viscosity increases, local Reynolds number goes down. Rho u L by mu. When the Reynolds number goes down, flow tends to become laminarized. What does it mean? It means any disturbance in that hot flow will die down quicker than what happens in the case of that with lower viscosity. With lower viscosity, it means it is able to sustain the oscillations. In the higher viscosity case, it dissipates much more, much faster. Okay. So, we must keep this variation in our mind. So, what may happen when you discuss effects of turbulence, we must keep this in mind. Under strong turbulence, the flame structure itself is altered. Now, what is meant is that if the velocity fluctuation and length scales are such that they are comparable to the flame thickness, then you will discover the flame will be, structure itself will be affected. What do you mean by flame structure? You saw in this, you remember you saw here in 0.5 mm, the whole thing is changing. Now, suppose this length scale of turbulence is 0.2 mm, it means it will distort this. So, the distributions which you see here are no longer correct. It is far more difficult to analyze this, but not so difficult to analyze the wrinkled flame, because you can imagine that it is a question of how to account for the wrinkling effect. Okay. So, many people have put in their effort and time in measuring the flame speeds and analyzing them. This is a very important diagram connected with this, where you see turbulent intensity scaled with the laminar flame speed with the length scale of turbulence divided by the flame thickness for unstrained flame thickness, which we have been talking about. The line here RE equal to 1 and this is a very important length scale, below which you will find laminar, beyond which you will find many other behaviors. You will find here the so-called wrinkled flame rate, which we discussed just a few moments ago, and you keep increasing the intensity, then it becomes corrugated, distributed reaction zone, and in a final stage, when everything is well mixed, you will get a well stirred reactor, which we may not have discussed at the moment. Stirred reactor is one limit of the whole thing, where fuel and oxidizer elements are completely mixed with turbulence. So, you will get at any one length scale, if you keep increasing the intensity, you approach well stirred reactor. Okay, there are many other behaviors which are presented here, which we may come back and discuss later. And these length scales are essentially Kolmogorov length scale and Taylor length scale, inertial scale. All these again will come back and address them later. Let's look at the results of on premixed mixtures, both laminar and turbulent. Laminar you saw here, and you see here the role of turbulence. U dash by SL, again length scale divided by the flame thickness. You will find that the reaction, the various zones are shown here, the corrugated flamelet, thin reaction zone and the broken reaction zone, and you will find the turbulent flame speed as a ratio of the laminar flame speed, experimental data, and a large number have put their mind into getting correlations. You see the number of people who have put in their correlations is humongous, about 25-30 people have put in their correlations. Only conclusion we will see in a moment. All experimental data, and I could fill this whole page with large number of data from various people. There are still broad variations are okay, but predictions are never okay. You will find so much of data in these places, and the conclusion is that of not only one, several people, the correlations for turbulent flame speed are not satisfactory. Modeling of the role of turbulence needs substantial improvement for premixed flames. Well, quite often it is said that for complex premixed flows, a simple approach is to use Bray mass dB. This is somewhat of a simple model, like we discussed for the diffusion flame, where you have the states which are involved or the progress variable in which you have fuel going to the oxidizer. The flame is only at one location, stoichiometric location. Here you say there is flame or no flame. There is a thin zone. On one side is premixed mixture, on the other side you have essentially burnt products. And this is a thin flame, thin premixed flame. There is no structure in it. What all you can do is to actually see how the flame moves around in a situation where chemistry is not involved. You are only looking at zones where there is fuel or oxidizer are present or burnt products are present. There is a model involved as to how the flow turbulence has to capture it. It is a substantive study, and there are codes which account for it as well. Okay.